Hello, I'm Tatiana Maiskaya.
And I'm Arina Nikandrova.
And we're going to present our paper entitled as Privacy Paradox When Hiding in Plain Sight Works. Nowadays, a lot of people willingly share their personal data over the internet. We seem not to be bothered by how many people will see our personal photos on Instagram or Facebook. For example, according to statistics, 63% of Facebook profiles are said to be visible to public, that is, to the whole world. Well, this couldn't have gone unnoticed by entrepreneurial tech geniuses. In 2012, Moscow-based IT company called i3 developed an app that, without exaggeration, shocked the world. The app is called Girls Around Me, and it doesn't just tell you where all your friends and co-authors are. It tells you where all nearby single women are and allows you to see their full name, photos, and even send them messages. This was a wake-up call about privacy, as the app didn't do anything illegal. All it did was to merge Facebook and Foursquare data that was already publicly available and laid it over Google Maps. After such public backlash against this app, one might expect that people would change their online behavior and choose to restrict their accounts in social media platforms. But no, all the blame was laid on Facebook, Foursquare, and Girls Around Me developers. And up to this day, a lot of profiles remain public. Should we see it as a foolish, blame-shifting behavior of people who cannot understand privacy settings? In this paper, we show that there is more to it, and such behavior might be perfectly rational.
A general framework that we consider is as follows. The game is between a hider and seekers. At the outset of the game, the hider publicly commits to the number of seekers, denoted by N, who have access to the hider and can learn about her. We interpret N as the strength of privacy protection that the hider chooses. Higher N means lower protection. In practice, the hider can control the number of seekers by, for example, limiting the size of the press pool with direct access to her, or by choosing who to be friends with on Facebook, or by limiting the number of online platforms on which to be active. They restrict the hider to choose at least one seeker, thus assuming that a perfect protection is not feasible. After committing to the number of seekers, the hider gets involved in a story which can be one of two types, either compromising or non-compromising. The story type is private to the hider. The seekers aim to find and expose only compromising stories. Each seeker can uncover the story by undertaking costly learning. The hider chooses the number of seekers to maximize the probability that the seekers fail to find and expose her story when it is compromising.
Our focus is on the optimal number of seekers. The main trade-off that the hider faces is between the direct and the indirect effect. According to the direct effect, an increase in the number of seekers increases the probability that the seeker's learning reveals a compromising story during a time interval of fixed length. Obviously, it hurts the hider. In contrast, the indirect effect reflects the change in each seeker's learning strategy. In particular, larger N increases the speed at which each seeker becomes more pessimistic that the story is compromising. Speedy belief updating discourages the seekers from learning, which benefits the hider. It turns out that when the discount rate is sufficiently low, the indirect effect takes an upper hand over the direct effect, and the hider optimally chooses the open access policy with infinite number of seekers. Intuitively, when there are many seekers, each of them would give up learning sooner, thinking that, well, had the story been compromising, others would have found it already. This striking result is reversed when the discount rate is high, because impatient hider places more weight on avoiding a compromising report now, which is captured by the direct effect.
In our model, by controlling the number of seekers, the hider effectively controls the number of independent information sources that transmit information about her. Each seeker has access to a dedicated information source and decides how much resources he is willing to spend on listening to this source. The hider takes the properties of these information sources as given. In particular, a source is characterized by two parameters. The first parameter determines the protection of compromising stories, and the second parameter determines the protection of non-compromising stories. We interpret these parameters as exogenous privacy protection and treat them as policy instruments. In contrast to the first result, our second result says that the hider benefits from stronger exogenous privacy protection. In reality, exogenous privacy protection measures are established as part of accounting rules or cultural norms or offered by the government or private companies. In our example, exogenous privacy protection is controlled by Facebook and Foursquare. These platforms gave APR access to their data and made it possible for Girls Around Me app to organize public information in a way that made it easier to find, thus relaxing protection of that information. Thus, our results justifies public accusations of Facebook for insufficient privacy protection, and in general calls for stronger privacy laws, which is the main policy implication of our model.
These two results together provide a rational explanation for the empirical phenomenon called privacy paradox, which in particular was manifested in the debates around Girls Around Me app. It refers to the empirical observation that people often claim they value privacy a lot, and yet they behave as if they don't value it or value it very little, for example, by leaving their profile visible to public. The first result explains the second half of the sentence. People often behave as if they don't value privacy, as they should according to our model, because the open access policy is optimal for the hider. The second result explains the first half of the sentence. People still value privacy a lot, and here and there we hear complaints about insufficient privacy protection legislation. This is perfectly rational because the hider always benefits from stronger exogenous privacy protection.
The formal model goes as follows. At the outset of a game, the hider publicly commits to the number of seekers n. After that, she gets involved in a story of type theta. When theta is equal to 1, the story is compromising in nature. When theta is equal to 0, the story is non-compromising. The seekers know neither the hider's story nor its type, but they can undertake costly learning to uncover it. They share the same prior belief that the story is compromising. Each seeker is endowed with information source that fully reveals the story through a Poisson process with rates mu1 if a story is compromising, and with rate mu0 if a story is non-compromising. Learning is costly. The flow cost of learning is C. Conditional on the story's type, the information sources of the seekers are independent. Parameters mu0, mu1, and C are exogenously given and known to all players. Our model features private learning because we assume that the seekers do not observe whether other seekers are learning and do not observe their learning outcomes and do not communicate with each other. The story becomes obsolete through a public Poisson process with a arrival rate rho. A story that has not become obsolete yet is called an up-to-date story. Given the payoff structure that we'll describe in a moment, neither the hider nor the seekers care about obsolete stories, and so the game effectively ends once the story becomes obsolete. Thus, we can interpret rho as a discount rate that is common to all seekers and the hider.
Each seeker has an option to report the story, but only after learning it. The payoff from not reporting anything is 0. Reporting a non-compromising or obsolete story always leads to a negative payoff, and thus such stories will never be reported in equilibrium. The only way to get a positive payoff from a report is to report the story that is up to date and compromising. Moreover, the story must be new in the sense that it has never been reported before. Hence, the seekers are essentially participating in a winner-takes-all contest with uncertain prize. The first seeker who finds the story gets the prize, which is valuable only if the story is up to date and compromising. All reports are public, and so the game effectively ends after the first report. The hider's objective is to choose the number of seekers n to maximize the probability of avoiding the report of a compromising story before it becomes obsolete. The cost of lowering N is 0, and so it's, as you can see, not included in the hider's objective. We make this assumption to avoid a trivial conclusion that weak protection, that is, higher N, is optimal just because the protection is costly. However, we make two assumptions that preclude perfect protection and make the hider's problem non-trivial. First, we assume that the hider has to give access to at least one seeker. And second, the parameters of the model are such that each seeker finds at least some learning optimal.
Here's a plan. We start with analyzing the seeker's game for a fixed number of seekers. Then we move to the hider's problem and solve for the optimal number of seekers. At the end, we will talk about policy implications and related literature. Consider seeker I. For him, the game effectively ends at random time tau I, when the hider's story becomes obsolete, or seeker I discovers the story, or one of other seekers reports the story, whichever happens first. Prior to tau I, at each moment t, seeker I privately chooses learning intensity, which we denote as xit. We focus on a symmetric equilibrium for the seeker's game, where all seekers use the same learning intensity, which we denote as x star t. Then prior to tau I, seeker's I subjective belief that the hider story is compromising changes according to the following law of motion. When the story is compromising, learning outcomes are effectively public because any discovery immediately leads to a public report. Hence, learning rate includes intensities of all seekers. In contrast, when the story is non-compromising, learning outcomes are private because it is not optimal to report non-compromising stories. Hence, learning rate includes only seeker I's own intensity. On the equilibrium path, the beliefs of all seekers who are still learning coincide. We call it common equilibrium belief. However, out of equilibrium, seeker I's learning intensity might be different from the equilibrium intensity, and thus the subjective belief and the common belief change differently. We restrict attention to Markovian strategies, by which we mean that seeker I's learning intensity depends only on his own subjective belief and other seekers' common equilibrium belief. Then the equilibrium intensity becomes a function of common belief, and in equilibrium, this intensity must be equal to seeker I's optimal strategy. Substituting the intensities into the belief updating formula, we get evolution of beliefs on a two-dimensional space. So we will be depicting the evolution of beliefs on a graph with subjective belief on horizontal axis and common belief on vertical axis.
If the arrival rate of a compromising story is higher than the arrival rate of a non-compromising story, then no matter what the intensities are, both the subjective and the common beliefs are unambiguously decreasing over time. In that case, the equilibrium isn't pure strategies. And so the seekers learn with intensity 1 until their common belief reaches some threshold, which we denote as P upper bar. At this threshold, each seeker is indifferent between learning and stopping. And so the flow cost of learning, C, is equal to the expected flow benefit given by the product of the instantaneous probability of uncovering a compromising story, mu1 times P upper bar, and the payoff of 1 from reporting it. If n mu1 is less or equal to mu0, then the common belief is increasing and the subjective belief is increasing if seeker I is learning, no matter what the equilibrium intensity is. In that case, the equilibrium in pure strategies does not exist, and the seekers use interior learning intensity for intermediate beliefs. The lower threshold is calculated from the indifference condition for a single seeker, conditional on other seekers stop learning. In contrast, the upper threshold is calculated also from the indifference condition for a single seeker, but conditional on other seekers learning with intensity 1. And these thresholds do not coincide because competition from other seekers reduces the expected payoff from learning. The fact that these two thresholds are not the same explains why equilibrium in pure strategies does not exist in this case. When the belief is between these thresholds, each seeker strictly prefers learning when other seekers do not learn, and strictly prefers not learning when all other seekers learn with intensity 1. This intermediate intensity comes from the equilibrium condition that guarantees that the beliefs are moving exactly along the diagonal. In the remaining case, the common belief is decreasing, but the direction for the subjective belief depends on the equilibrium intensity. Nevertheless, the equilibrium takes a familiar form, which is similar to the previous case. But there are two differences. First, the common equilibrium belief is moving in the opposite direction, and so over time, the seekers become more pessimistic. And second, the expression for the upper threshold is different. The lower threshold and the intermediate intensity are the same.
Now, armed with equilibrium in the seeker's game, we can move to the hider's problem and solve for the optimal number of seekers. We'll start with a case when there is no discounting, that is, the story never becomes obsolete. Moreover, let's start with a growing pessimism case, in which compromising stories are easier to find than non-compromising stories. That is, mu0 is less than mu1. In this case, the seekers become progressively more pessimistic that the story is compromising and eventually give up unsuccessful learning at belief threshold P upper bar. When all seekers learn, a compromising report comes at rate n multiplied by mu1. Hence, the probability that the seekers fail to report a compromising story is given by this expression, where t is the time that the seeker's belief takes to reach threshold P upper bar from the prior. In other words, t is the duration of unsuccessful learning. This time is derived from the belief updating equation. And so in the denominator, we have the speed of learning given by n multiplied by mu1 minus mu0. The optimal n balances two effects, the direct effect and the indirect effect. The direct effect comes from the reporting rate. It says that an increase in n increases the probability that the seeker's learning reveals a compromising story during a time interval of fixed length. Hence, the direct effect hurts the hider. The indirect effect comes from the speed of learning. It says that an increase in n increases the speed at which each seeker becomes more pessimistic that the story is compromising. Speedier belief updating reduces the time that the hider is subject to the seeker's attention, and so it benefits the hider.
Substituting the time, we get the following expression for the probability that the hider maximizes. This is the formula for the case when mu0 is less than mu1. If mu0 is greater than mu1, then the formula for P is almost the same. If n is less or equal to this ratio, mu0 over mu1, then we are in the growing optimism case, where the seekers never stop learning until they uncover the story. And so the hider has no chance of avoiding a compromising report. To revert the direction of belief updating, she chooses n that is greater than this ratio. And so the seekers become progressively more pessimistic that the story is compromising. And in this case, the expression for P is similar to the previous case, with the only difference in the belief threshold. But in contrast to the growing pessimism case, here the seeker's common belief never actually reaches this threshold, but drifts towards it with diminishing intensity. Nevertheless, the part that depends on n is the same in both cases, and so we have the same direct and indirect effects that work in the opposite directions. It turns out that the indirect effect always takes an upper hand over the direct effect, and together they always call for the open access policy, that is, n is equal to plus infinity. To see this, observe that maximization of p is equivalent to minimization of this ratio, which is decreasing in n, and so n is equal to plus infinity is optimal.
The introduction of positive discounting helps to disentangle the direct and indirect effects. If a discount rate is sufficiently low, that is, the story remains up to date for a long period of time, then minimizing the duration of learning, or more precisely, minimizing the cumulative learning intensity, is more important than minimizing the instantaneous learning intensity, which determines the instantaneous probability of a compromising report. So when discount rate is sufficiently low, the indirect effect prevails, thus which makes open access policy optimal. If a discount rate is sufficiently high, that is, if a story becomes obsolete quickly, then minimizing the instantaneous learning intensity is more important than minimizing the cumulative learning intensity, and thus the direct effect prevails, which makes the strongest feasible protection with a single seeker optimal.
The HIDA takes the arrival rates of compromising and non-compromising stories as given. We interpret them as exogenous privacy protection and treat them as policy instruments. We show that the HIDA becomes worse off when exogenous privacy protection weakens either through an increase in mu0 or through an increase in both mu0 and mu1 by the same amount. In other words, the HIDA always benefits from an increase in exogenous protection, which gives us the main policy implication of our model. The society that has the HIDA's interest at heart should have strong privacy protection laws as part of exogenous privacy protection. Note that the HIDA benefits from stronger exogenous protection even if she optimally chooses the open access policy, thus behaving as if she doesn't value privacy. And that explains the privacy paradox.
The paper that is closest to us is Akziget and Liu, who also study private learning with Poisson bandits, where, similar to us, players do not share bad news. The main difference is that Akziget and Liu assume that the rate of outcome arrival is independent of the outcome type, which implies that no news is a bad news, and players become progressively more pessimistic over time. The unambiguous direction of belief updating guarantees the existence of equilibrium in pure strategies. In contrast, in our game, the arrival rate varies with the outcome type, and so the direction of belief updating may depend on the learning strategies of others, in which case there is no equilibrium in pure strategies. Solving the game in this case is technically non-trivial, and we cannot use the off-the-shelf results on viscosity solutions, which are typically used for this kind of problems. We view the approach we propose as our technical contribution.
To conclude, we study a model where the HIDA optimally chooses to open access to infinite number of seekers, thus hiding in plain sight. This behavior is optimal because when many seekers are searching for a story, the absence of finding quickly discourages them from learning for a long time, because had the story been compromising, most likely it would have been already reported. This result, however, doesn't mean the HIDA does not value privacy protection. She always benefits from a stronger uniform protection of all information as modeled by the arrival rate of a story.